So let me show you how to solve friction problems first. Let me show you how to solve for the force of friction first. Then we'll solve problems with friction. I'll do the world's best example. Okay. So first, the concept of what is friction, right? Right. Friction is the force to slide one object, like this box, across the other object. And let's not confuse things. Let's slide it at a constant velocity. Why aren't we going to accelerate it? I mean, we will accelerate it, but at first, why aren't we going to accelerate it? Yeah, to negate like the F equals ma sort of thing, right? In other words, if there were no friction force, if this thing were sliding on like an air film, like those air track gliders that I've shown you, it would still take a force to make it accelerate. So we're talking sliding it at a constant speed, okay? So if I'm going to slide this block here at some constant speed across this surface, what is that force needed to do that? Okay? There we have it, right? Okay. What does it depend on? What do you think it depends on? How heavy it is, right? Okay. Heaviness. What else is it going to weigh? I suppose I should write the word weight up there, shouldn't I? Heavy. What does it depend on? Heavy. Okay, it depends on the weight. What else does it depend on? The type of surface, right? And right now, by the way, I'm supposed to say, good, you've come up with all of the things that it depends on, because our model is going to be based on that, and everybody teaches friction this way. What else could it depend on? Well, okay, incline and stuff like that, but those are just like other forces that act on it. When you incline the plane, right, gravity acts along the plane, and so it's friction is still friction, but, you know, and if we're accelerating it, that's not friction, it's just the inertia, right? Okay. What else can it depend on, do you suppose? How about this? Is this block going to be the same if I do this? Well, it's surface area, right? I just changed the surface area. And possibly, by the way, also the smoothness of the surface and all this stuff, right? So we don't think it depends on area, okay? Does not depend. Okay, we don't think it depends on area. And the rationale is this: if we decrease the surface area, we've got less area, but we've got more pressure on that area, right? If we increase it, we've got more area, but less pressure on all that area, right? Okay. We also, the other major thing is that we don't think it depends on speed. Okay. We don't think it depends on speed. I'm pretty sure that that's kind of nonsense. Certainly with air friction, that's what it does depend on, is speed. Okay. So I don't know about sliding on a surface, but I think for low speeds and for most surfaces, this is true. Kids that have done experiments like an IB where they try to change the surface area, nothing happens, right? So the kids have done experiments with that, and there you have it, right? So this is it. Now we need blah, 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 demonstration. Is it rough or smooth? Not supposed to depend on. We've got that, okay? So now we need a formula for it, and this is our formula. Oh my God. Okay. The force of friction, okay, is equal to some Greek letter times an F with an N. I don't know, what is that? Okay, well that's the force of friction in newtons. Okay. That is the coefficient of friction. Now, it's the Greek letter mu, which is spelled mu. Right? But apparently you pronounce this mu. Okay? So it's the Greek letter mu, and it's the coefficient of friction. It is something that you look up. It corresponds to the roughness of a surface. So 0 is slippery. Okay? 1 is a clean rubber tennis shoe on a clean basketball court is a 1, okay? Which, by the way, human ligaments and stuff are not used to that much friction force, and that's why basketball players always get like knee injuries and stuff like that because they get too much friction, right? So the coefficient of friction is somewhere between 0 and 1. I guess we could say, yeah, greater than or equal to, right? So 0 is that air track cart there, where it glides on a film of air. 1 is you're trying to drag a piece of rubber. Now, obviously, if you glue the thing down, if you get like one of those, you ever got those mouse traps that just like the mouse sticks to it and can't get off? You ever seen those? It's like amazing. If you had one of those, it would not obey this law. Okay? Yeah. In fact, okay, my mom, a bird flew into my mom's house down the chimney, because they sit up by the flue because the warm air comes up there, right? This is Minnesota. Flies into her house. I go to catch the bird, so I throw a towel over it. I hit the bird. It falls right on top of one of those mouse traps. Like 2/3 of the feathers on its entire body are stuck to that mouse trap, right? I'm like, oh no, I've just ruined a bird, right? But what I did was I just grabbed the bird and I very slowly pulled it apart, like duct tape. You know, duct tape you can do it very slowly. You can peel a label really slowly without tearing it. And it took like a long time, but I got all the feathers, like maybe 1 or 2 little downy feathers stuck to the thing. Let the bird go. I was like, I'm out of here. So coefficient of friction, this is sticky. This is slippy. Yeah? And you look these up in the book. You look them up in the book, or I give them to you, right? They are not, by the way, universal constants like the density of lead or the boiling point of water at 1 atmosphere, okay? They're nothing like that. They're highly arbitrary, and when we look at them, we can sit there and criticize them and everything like that. But in general, in your textbook, if they give you a friction problem, find it somewhere in the book. You'll find a table of coefficients of friction. Okay. On my problems, on my worksheet, I'll tell you what coefficients to use. But just suffice it to say that 1 is something that's very hard to drag. 0 is something that's extremely easy to drag. Okay. And then this thing here is the normal force. It's the force exerted by a surface to maintain its integrity. Well, let's think about that, right? If gravity pushes this thing down against the surface, right, does it accelerate down? No, so the sum of the forces vertically has to be 0, correct? Okay, that means the surface is pushing up on the box, yes? Okay, in fact, that's what surfaces do. That's the purpose of this counter. This counter is a device that pushes up on things, isn't it? I put this on there, gravity's trying to pull it toward the center of the earth, and the counter pushes up on it, yes? Yeah, go to a furniture store, seriously, and ask them. I say, I need one of those things that pushes up on your butt. And they're like, yeah, like, you know. Of course, we're talking about a chair, right? Right now, you're sitting on a chair. Gravity's pulling you down against the chair, and the chair's job is to push up on you, yes? It's kind of more comfortable that way, more comfortable than standing around, right? Okay, so that's what we're talking about. Now, aren't these guys equal? This is the weight. The weight and the normal force are equal. And so I'm just going to cut to the chase. Okay, here's the chase, right? It's just mu times m times g. What's mg? Mass times gravity. That's the weight, isn't it? Yeah. So this guy really is the weight, the normal force. And for all of our problems, it's just the weight. Now, the only time it's not is if you like tilt the surface, or if you set up a clever system of pulleys and levers, right? Where I lift this thing up slightly, but I don't remove it from the surface. I don't know why you would do that, but if you did, then the force pressing those together is not the weight. Or if you're sliding something like along this whiteboard here, well, the friction force to slide along this whiteboard depends on how hard I press on the whiteboard, right? And it's not the weight of my hand, it's just how hard I press. Yeah. Okay, so in general, it's how hard the surfaces are pressed together. For all our problems, it's going to be the weight, so that's why I put the little mu mg up there. Here's another picture of that, right? You apply a force like this, and a lot of problems are like this. You apply some force to the side. The force of friction is opposing the motion. So friction always opposes velocity. Right? If it's sliding, it's always the force that opposes velocity. So gravity is down, the normal force is up, the applied force is sliding it this way. And it says mystery and surprise, which is one of my favorite things about this. So here are some coefficients of friction that we can look at. And I scanned these out of, because this is a better table than I found in your book. So I found this, and this is the IB textbook. But there we go. So wood on wood. And notice that some things, let's first look at this right-hand column here. Some things are slippery, right? Like Teflon on steel in air. Wow, Teflon's really slippery, right? In fact, they make these little street hockey pucks that run on little Teflon gliders. They slide across the ground. They're better than balls. When you